always forget about the microphone till I begin, because until I have to start saying anything, I'm not saying anything. And if I'm not saying anything, I'm not thinking about the microphone. All right. One's trickling in here. Got Natalie, Gabriel now. And is that it? I didn't think so. Aha, there's Alex. And Kaylin. See, I know, just give them 30 more seconds. All right, now everybody's here and we can begin. Good morning, everybody. Today we've got a super sweet topic for you, the end of our short, brief study of logarithms and exponential functions, dealing with those. And now we get to the juiciest bit, the natural log, based on that most mysterious of numbers, E. Wait a minute, Mr. Apple, E is a letter. Yes, I know. But E is also a very wonderful number. So, remind ourselves where we were. We have been going through, yesterday we talked about various properties of logs, ways you can combine logs and use them as shortcuts to break up, reduce the level, as it were, of relationships between two numbers, turning multiplications into additions and so forth. And all of that is going to carry over into today. I hope you checked your work on these exercises. Remember the, oops, give me the laser. There we go. We'll go with blue, sure. Remember the answers for these are at the end of the packet. Answers, right? Section 2. There's no need for me to go through them. You have them yourself, okay? You should be using that. Anyways, so back to today, our continuation is into the natural logarithm and exponent, because of course all the other ones have been artificial? I don't know. I don't know why it's called the natural log, but other than it is a number that does occur in nature, and it seems to come up very naturally as mathematicians were going along. They, of course, discovered this constant before they really came up with a name for it, and like, hey, we keep running into this 2.7 something. What's up with that? Very interesting history there. So the natural log, often written as ln, okay, so L for log, N for natural. The letters are, of course, backwards because I'd probably blame the French for that one. Which you may have noticed on your calculator. There's a whole separate ln button. It's a wonderful button, very useful. And the ln of x is simply the log base e of x. All right, e, of course, symbolizes a very special mathematical constant. We'll get more into it in detail in a moment. And it's, in general, it's important for growth and decay problems, right? Which is one application we've hinted at of exponential in general. But if you want a real application, right, the real model of actual real-world data, you'll need more than just any old log. You need a natural log. The logarithmic properties listed above hold for all bases of log. Let me highlight that again. The logarithmic properties hold for all bases of logs. This, of course, would include base e. So everything we just did still holds up. Don't change any of that. The only difference is, instead of randomly having little base b there, we now have little base e, and so honestly on the exercises it's not really going to feel that different. You're just writing a different letter. And I can't really fix that, as it were, but it's not really broken. It shouldn't feel any different. However, if you see, and there's a mistake here with the packet, please cross out log x there and put ln x. If you see ln x written with no base, the natural log is implied. Okay? If you see logx with no base, it actually implies base 10. That would be the common log. Okay? The common log is the one where we've decided, that's log enough, we don't need to write the base every time, we'll just leave it as 10. That's the implied one. Unless you're talking about like a real specific circumstance within a textbook where they have said from the beginning, we will use log to mean the natural log. That does happen, but they have to say that ahead of time. Your calculator button that just says logx, that defaults to log base 10, okay? So that's the more general rule. Now, there's the thing with that number e. It cannot be written exactly in decimal form, just like pi. All of our approximations, right, are merely that, approximations. You can go as many decimal places as you want, and you're still not quite perfectly there. But good enough for our purposes, 2.718. Think about that, just like pi, 3.14, let's go a little more, 3.14159. E, 2.718. Okay. Of course, all the properties of logs we have written down also apply to the natural log. They said that again. It's almost as if it's important. And if we want to get particular, we can write them thusly. E to some number y is equal to x, and thus ln of x is equal to y. Of course, the e has been subsumed in the n here for the natural log. Those are our equivalent statements when dealing with natural log. And as usual, e to the 0, like any number to the 0, is 1. And natural log of 1, just like the log of any number, the log with any base of 1 is 0. So real quick, let's look through these examples given here. Just because we have an e there, we've got an e as our base. In the exponent itself is a log, also base e. You could have written this as ln of a. And so those operations undo each other. The exponent on the e is the log with the same base. It turns it back into a, right? Just like multiplying and dividing. And similarly, e times e to the power of a log e of x. Well, use our exponent rules. We know if I multiply log by something, I can put that as the exponent of the argument and vice versa. So now it's e to the log base e. Oh, well, let's use that, except now our argument is x to the a, so our answer is x to the a, right? Example number 3 here, log base e of e to the 2y. Again, exponent log rule, put the exponent out in front, 2y times log base e of e, all by itself. Now it has no exponent, it's just ln of e, which is just 1. So 1 times 2y is 2y. Pretty handy. And finally, log base e of x squared divided by 5. We've got division of the argument. Let's go ahead and split those up into 2 separate logs. 2 times log base e of x minus log base e of 5. This, of course, could be approximated with some decimal value. This stays as is because it contains our variable. Any questions on those examples? Okay, good, because they're not, honestly, that different from before. Again, we've just, instead of writing base b, we're now writing base e. What's the big deal? It is a big deal. The number e is huge and magnificent. And I cannot even begin to fully explain all of the wonderful sights and sounds and smells that accompany such a number. So instead, I will turn your attention to a video here from a Mr. Zackstar. And it says connected to AirPlay. I'm not sure what that's going to do for my capture here. I do not want it connected to AirPlay. Don't do that. I just sworn I had this working before. Not now. Where are you sending it? I just want it on my screen because I'm copying my screen. Where is it going? Well, so much for having it up on the old iPad. All right. Give me one moment. I'm going to draw it up here on the computer.
This video is sponsored by...
Okay, there we go. And so we will have to capture that. Okay. And you guys need a share screen to share the computer sound over Zoom.
Brilliant. 2.7182881 and so on. This is E, or Euler's number. And I remember when I learned this in high school, I thought, when would that even show up in the real world? But now I realize the better question is, when doesn't that show up? Or at least that...
Right? Where is this number? What's the big deal? It's so-called natural log. Does it actually appear naturally? That is what he is going to address. So, to here.
That feels like a fair question. Now, mathematically, E is just what you get when you calculate 1 plus 1 over a really big number to that same really big number. And as that number gets bigger and bigger, you get Euler's number.
Hey, look, limits. We've been talking about this, right? This is one reason why they're kind of necessary. There's literally no other definition of E. There is no way to actually find it except by this method. And since we cannot practically actually get to infinity, all we've been able to do since the first discovery of this number is to get closer and closer approximations. I think I just looked on Wikipedia, we're up to like the 10 billionth, no, trillionth. I believe it's in the trillionths of digits, you know, with supercomputers and whatnot.
Now, if you're in high school and just learned about this, it's probably because you're in the compounding interest part of the curriculum, which is where I'm going to begin. So let me first try to intuitively explain what this seemingly random number really is. Imagine you put $1 in a bank that pays out 100% interest per year. That means after 1 year you'll have $2.
Best bank ever.
But that's only if the interest compounds once a year. If instead it compounds twice per year, then that means you get 50% after 6 months and another 50% after 6 more months. So after that first 6 months, you'd have $1.50, and after another 6 months, you'd get 50% of that, which would leave you with $2.25, a little more than before. If instead the interest compounded 4 times per year, then you get 25% every 3 months. The first payment would leave you with $1.25, then 25% of that leaves you with $1.56, another 25% gives you $1.95, and the final 25% gives you about $2.43. So notice that the final value keeps going up. If the interest compounded daily, we'd end up with a little more than $2.71, and as we keep going up to compounding every hour, second, microsecond, nanosecond, and so on, the amount in your bank would become E dollars after a year. Now,
Okay, you with us so far, right? The more frequently you compound, the more times you stop, check, and be like, oh, you've earned so much interest so far, let me add that to your account. Because then the next time you check, that interest is affecting the interest that was just added, hence the compounding effect, right? The interest of the interest. This is why your student loans can get greatly out of control. Anyways, right, so it seems like that should go up and up and up. It should just be increasing more and more, but there is a limit to it because the more frequently you compound, well, the smaller time period has passed and thus the smaller the amount that has been added. So it doesn't go up to infinity, unfortunately. It reaches this limit of E for whatever reason. Right? Questions so far?
That's what we learned in high school at the minimum. But now let's see the other times that E shows up across math and science in ways that usually have nothing to do with compounding interest. And I'm going to start with some more random examples, the first one being probability. Let's say there's a 1 in a million chance of winning the lottery. If you then play the lottery a million times, your odds of losing every time is about 1 over E, or 36.8%. Well,
okay, so get that straight, right? Your odds of winning were 1 in a million. You played 1,000,000 times. And I know your first instinct is to say, oh, well, then I should expect I would probably win 1 time out of those. Not quite. You would win, your chance of winning once is slightly different than that, right? The odds of losing every time is about 36.8%, 1 over E. So your odds of winning that exact once is about 1 minus that. There are, of course, probability that you could win twice and 3 times and 4 times. So it's an interesting take and not something we usually consider. But remember, sometimes in probability, you want to know, well, what's the probability that I would win once or twice or 3 times? Any wins, right? Multiple wins are great. So it's easier to sometimes calculate what you don't want and then just subtract from that. And it turns out it brings up this E again.
Approximately, and this will always be the case for games with small probability. The reason for this is because a 1 in a million chance of winning means you have a 0.999999 chance of losing, or 1 minus 1 over a million. Raise that to the 1 million, and those are your odds of losing every single time. And as this value gets very large, since we have a minus sign this time, the whole thing will approach 1 over E. Then next up, imagine a party where everyone brings an umbrella. After the party's over, people are in a rush and everyone grabs a random umbrella from the stack, not caring if it's theirs or not. The probability that no one left with their same umbrella is again about 1 over E, if the number of guests is pretty large. Another way to look at this is take a fresh deck of cards that's in proper order and shuffle it. If you do so randomly, there's about a 1 over E chance that no card is in its original spot.
No card is in the same spot, right? And this is, all right, is it really that practical of applications? No, we'll see more practical ones at the end. These are the ridiculous kinds of questions that only mathematicians would probably ask, especially with that umbrella thing. Nobody considers that at the party, but you get where we're going with this.
Next up, let's say you interview 100 people for a secretary job,
Oh, here's a good
and you
one.
judge them all by something like typing speed that can be given a value. Now, after each interview, you can either hire them or never see them again, and you're only going to pick one person. So how would you pick the optimal candidate? Because with each interview, even if the person has a fast typing speed, you never know if there's someone better that you just haven't interviewed yet. Well, the math says if you have 100 interviews lined up, first interview 100 over E of them, or about 37 people. However, you do not pick any of those first 37. You just keep track of who was the best. You will then pick the next person who is better than any of those first 37 people. And not only does E show up in the number of people you interview before making a decision, but if you follow this algorithm, you have a 1 over E chance of picking the best one. And this probability stays the same no matter how many people you have to interview. So even if you have 1,000,000 interviews lined up, just interview 1,000,000 over E of them, and then pick the next best person, and you'll have a 1 over E chance of picking the best one of those 1,000,000.
Okay, again, nobody's going to actually use that as their hiring practice, but you might set up a computer to make a selection from something based on certain criteria, where you would have a pool of 1,000,000 things, but the computer can check it in 5 seconds. Okay?
Now here's a random one. If you take a stick of length 10 and chop it up into 2 pieces, you get lengths of 5 and 5, whose product is 25. If you instead divide it into 3 pieces, you get lengths of 3.33 for each, whose product is 37.037. If you cut the stick up into 4 pieces, each length is 2.5, and the product will be 39.0625. And lastly, if you make 5 divisions, every piece is length 2, and the product is 32. Notice the maximum product happens when there are 4 divisions, which is also when the length of each piece is closest to E. That will in fact always be the case, as in to maximize the product, cut up whatever length you have into equal pieces, such that each piece is as close to E as possible. For the calculus people out there, to prove this, you can find that the maximum of some length divided by x times itself, x times, occurs at x equals that length over E. Now, if you're saying, wow, I really don't like how often E shows up in these random examples, then you're not going to like this next one. Imagine a function that is x to the x to the x, and so on forever, or the
Okay, be honest. How many of you, when you first heard about exponents, thought of this? Oh, well, what happens if you raise an exponent to an exponent? Right? I know somebody out there has done that. Right? This is what happens when you do that infinitely, exponent to the exponent to the exponent forever.
Infinite titration. Now, this will diverge for most values, of course. Like if you plug in 5 for x, this is obviously going to go to infinity. But it will converge for any x between 1 over e to the e and the eth root of e inclusive, which are about
What? Who comes up with this stuff?
and 1.4447.
Mathematicians, that's who.
So if you plug in something like the square root of 2 or 1.414, Since it's within those bounds, it will converge to a certain number. In this case, it actually converges to 2. But if you plug in something slightly out of the bounds, like 1.45, then it just goes to infinity. Now, moving on to
Bonkers.
this next example,
Absolutely
we also have the
bonkers.
Lexis exam, which is a university-level math competition that consists of what I think most would consider extremely difficult math problems. To set this up, we first pick a random number between 0 and 1. Let's say 0.682 in this case. Then pick another, we'll say 0.145. And we keep going until the sum exceeds 1. So right now the sum is 0.827, as in we need to keep going. If our next number is 0.394, our sum is now greater than 1 and we stop. Notice it took 3 numbers for the sum to exceed 1. Now if you did this with truly random numbers over and over, it turns out on average the amount of numbers you write down before the sum exceeds 1 is e.
You catch that? So if you ask all your friends to just randomly pick 3-digit numbers, right? And represent them as decimals between 0 and 1. And add up a selection of them, right? Until you go over 1. How many of these 3-digit decimals does it take to add up to just over 1? Sometimes it's 2, sometimes 3, sometimes 4. And on average, this is ridiculous. On average, it takes about E number of numbers randomly generated to add up to 1. Why? I don't know why.
And the competition problem was to prove that
crazy.
this was the case. E to the x also has, in my opinion, a very weird property that its rate of change is always itself. As in, if you were in a hypothetical rocket whose position was modeled by e to the t, where t is time, then your position, velocity, acceleration, and so on will always match.
This is a good one.
Which
Remember
means
this
when you're
for
at, let's say, the
calculus.
127 meter mark, your velocity would be 127 meters per second, your acceleration would be 127 meters per second squared, and so on. There's another interesting property when finding the area under e to the x, as the area from negative infinity to 1 is e to the 1. If we go to 2, the area is e to the second, and this would apply to any number. The majority of you who've taken calculus, I know this is obvious, but still interesting to think about. Now, probably the biggest reason that e is so applicable is because of this identity. Well, it's actually where this identity comes from, which is something known as Eulers Formula. I've explained where this formula comes from in a previous video, so I'm not going to do that again. But with the formula, you can see where that identity on the thumbnail comes from. Just plug in pi for x, and you get e to the pi I equals cosine of pi plus I sine of pi. Cosine of pi is -1, and sine of pi is 0, and thus we have our answer. With this formula, you can show some really weird math with imaginary numbers, by the way. I'm not going to show where these come from, but if any of you guys have a graphing calculator nearby, go ahead and plug in any of these, which look like they should give you a calculator error or something like that, but in fact they all equal real numbers that include e.
Go ahead, try it, right? It's great. I to the I, wait a minute, you can do that? Yeah, it's crazy. So if you want to try to understand why this might make sense, remember the intuitive use of imaginary numbers is as a rotation, okay? And trigonometric functions, which, hey, great transition into next semester, where we'll start our trig unit, are translating the connection between rotation and non-rotate linear transformations, right? So keep that in mind.
E and pi. Now, going back, what Euler's formula really does is relates an exponential function with e as the base to sinusoidal functions. And a typical sinusoidal function is seen in way too many applications to even name, from signal analysis to quantum mechanics, circuits, a simple mass on a spring, and so on. These all involve some sort of oscillation, which is why you can expect to see Euler's formula. I mean, if you just look at any circuits textbook, once you get to the alternating current section, all voltage inputs are sinusoidal. So when capacitors and resistors change the amplitude and phase of that input signal, it's harder to use traditional pre-calc math to represent the system. So instead we use Euler's formula to analyze everything. Like seriously.
See, look at this stuff, right? This is what you can expect if you go beyond just calculus, okay? So anybody thinking of certainly an engineering career or any STEM major, really, this is what you're going to have to look forward to, okay? Is that relation starting to relate exponential and trigonometric, and the connection number, the key to that is E, as well as complex or imaginary and compound numbers.
Seriously, it's everywhere in these textbooks. Or just look at an electromagnetism textbook. Since electromagnetic waves, including radio waves, visible light, X-rays, and more, are sinusoidal, we use Eulers Formula to represent them. And here you can see basically Eulers Formula with some more complexity in the exponent. And one of the most groundbreaking discoveries in math was that any function can be represented as a summation of sine and cosine functions. As in, if you add enough of them up, usually an infinite amount, you can create any other function that you want. In regards to audio and music, the Fourier Transform gives us the ability to analyze frequencies that make up a certain sound signal. And this is used for auto-tuning, removing unwanted frequencies or noise from a signal, amplifying specific notes, and more. The Fourier Transform is also useful in quantum mechanics, astronomy, optics, and so on, but signal analysis is definitely one of its most famous uses. And of course, if we look at the underlying math, it involves Eulers Formula. As some more examples of these real-world applications, when you let a block on a spring oscillate in some fluid, it will oscillate back and forth with a slightly lower amplitude every time. The envelope of this equation that kind of squeezes it to zero has an exponential decay equation, which includes e to some negative constant times time within it. Or when you take a pie out of the oven, it will eventually cool to the temperature of the room
Yes,
it's in.
finally, something delicious.
It cools down much faster at first, and then that temperature equation kind of flattens out over time, asymptotically approaching room temperature. This equation is that same exponential decay that has an e to the power of some negative value times time.
What? Okay, so there you go. Something you're all familiar with. Hot food cooling off. Okay? Starts out really hot, and then if you were to actually take the temperature, it would quickly get not nearly as hot because it has to do with the difference in temperature, right? It's really hot, but the room is not, and so the difference starts out really big, so it drops really quickly. But then once it gets down to about warm, it kind of stays warm and slowly cools off, slower and slower. That's what it's doing. It's exponential decay of temperature involving number E.
All right, now time for the weirdest part of this video. Here we can see the graph of x squared times e to the minus x. The area under it from 0 to infinity is exactly 2, which can also be written as 2 factorial. Now we'll graph x to the third times e to the minus x. The area under this from 0 to infinity is 6, aka 3 factorial.
Remember, factorial means multiply by all the descending digits, right? 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1.
And here's x to the fourth times e to the minus x, whose area from 0 to infinity is 24, or 4 factorial. So as you can see, the exponent here, factorial, will equal the area under the curve from 0 to infinity. Another way to write this is the integral of this curve
Why?
from 0 to infinity.
Because math is weird.
That exponent we see here, factorial.
Yeah,
and this
it's
takes us
crazy.
to the gamma function, which is written a little differently, but says the same thing. And what this is an extension of the factorial function. So if we wanted to find any integer factorial, we could just use this formula. But note that this equation could have anything in the exponent, not just integers. So if you ever see something weird like 1/2 factorial is the square root of pi over 2, it comes from this equation. In fact, if we go back to Desmos, I've graphed the equation and calculated the area under it from 0 to a big number, since infinity wouldn't work, as a function of z. So if we set z equal to 4, for example, we get 24, or 4 factorial, as expected. And if we set z to 3, we get 6, or 3 factorial. But now we can let z equal 1/2, and it spits out what would be 1/2 factorial, which, like I said, equals the square root of pi over 2.
Wait. We went in looking at applications of E, where it shows up in weird places. We got all the way to, hey, the exponential function can also be used to calculate factorials of non-integers. And if that wasn't weird enough, the factorial of 1/2 includes pi? What is going on here? Math is so weird and super cool. This is what I love about math. This is like, you just be playing with it, messing with it. Set up something ridiculous in Desmos. Play around with the sliders and be like, hey, wait, what? Where'd that come from? Why is it pi, right? I want to know why 1/2 factorial is square root of pi over 2. And this just, it's just this integral. That doesn't really explain it to me. This is something I myself want. Maybe this is what I'll do over break. I don't know.
And this is also another way to see why 0 factorial is in fact 1, because when z is 0, the area under this curve is 1.
Oh, there you
The
go.
gamma function shows up in quantum physics, astrophysics, fluid dynamics, and more. But from what I've seen, it's typically very advanced. Like, it can be used to calculate the volume of n-dimensional hyperspheres, or basically spheres in higher dimensions. Or on a paper regarding the Casimir effect, which appears in quantum field theory, the gamma function shows up several times in ways that I totally understand. And next to the gamma function, which itself has Euler's number within it, we have Euler's number showing up. So yes, this does have more applications than you may think. But now we're going to see what's definitely my favorite part of this video. We're going to go back to that hypersphere example, because there was something I found when doing research for this that just did not sit well with me. Let's say we calculate the volume of a sphere with radius 1 in every even dimension. As in we find the volume of a 0-dimensional sphere, a 2-dimensional sphere, 4-dimensional, 6, and so on forever, all with a radius.
Okay, reminder, we live in 3-dimensional space. Everything you draw on your paper is 2-dimensional, right? So you gotta work with me here. Out to 4 dimensions. What if there was another direction in which you could travel? That's where the 4-dimensional sphere exists. Okay? If you don't have a good grasp on that, read Flatland.
Radius of 1. And yes, in 2 dimensions, for example, a sphere is really just a circle, and volume really just refers to area. In this case, it'd be pi. But we're just using sphere and volume as general terms because of the higher dimensions. Anyway, if we add up the volumes of all those even-dimensional unit spheres forever, the summation would equal e to the pi. And no, I'm not joking. But the applications of Eulers number...
Wait, what? You took all of the, the 2-dimensional one, the volume is just pi, the area, because it was radius 1, right, unit 1. And you add up all of these, some multiples and involving pi, and you get e to the pi?
Numbers still don't stop there. Like the classic normal distribution or bell curve we see all the time contains Eulers number. The Laplace transform that's used to simplify calculations for things like circuits and control systems also includes Eulers number, and I could go on for a while. But if you want to keep learning about these unique areas of math and their applications, like with Eulers Formula and imaginary numbers, you can continue to do so at brilliant.org, who I'd like to thank for sponsoring this video.
Okay, and at that point we will stop there because he's sponsored by Brilliant, I am not. So thank you, Mr. Starr, that has been fantastic. All right, and where's the stop share button? There we go. Okay, so there you have it, right? E, crazy, ridiculous, super applicable in everywhere that you will, basically anywhere that you will be using math actually in a career, E is going to show up. I mean, beyond, simple arithmetic level, right? Okay, I hope that's been interesting, tickled your brain a little bit, even if you didn't understand it all. I didn't understand it all, that's okay. Okay? The point was, hey, it's used places and it's weird but interesting, okay? If you got those 3 things out of it, then you're good. Otherwise, your work for today is to complete these 2 exercises. Okay, they have a lot of parts to them, all right? But it's just, again, logs and exponents, but now we're throwing in the E on top of it as our base. And the first step is practice with that calculator button. Okay? Get those decimal approximations. Please go at least 3 decimal places on all of those. Otherwise, does anyone have any actual questions? Oh, Alex, I didn't see yours because the chat wasn't showing up when I went full screen. E always equals to 2.718. Well, 2.718 is 3 decimal places for E. But yes, it is a constant. It's always that same number. So 100 over E for all the probability questions, yes, is 100 divided by 2.718. You could keep going with more decimals, but yes. Okay, then we will leave that there. Go ahead and use the remaining class time to finish up those exercises. And I will see you next week, or you will see me, to work on final review. We're at the end.